and a Bachelor of Arts from Yale, and she earned her master's at MIT. Prior to graduate school, she worked in the area of AI safety and governance. Thanks for joining us, Andi. Take it away.
Awesome. Yeah, thank you guys for inviting me. Super nice to meet some new folks. Um, so yeah, I think today we'll keep it casual. We'll talk about a recent line of work and how we think about learning useful qualities for robotics from humans. And then we can kind of, pontificate away at the end and see if there's any interesting ideas that we can take away for future work. Yes, so I am coming from MIT, and I have the pleasure of being kind of co-advised by a robotics faculty member as well as an NLP faculty member. And so I think in addition to thinking about how to build general purpose robots, I think a lot about how these robots need to interface and communicate with humans. And so I think the thesis of a couple of works that I'll present in this talk focus kind of centrally on the idea of learning good abstractions or preferences from humans. Cool. All right. So maybe like one day in the future, I invite you all to my house, and maybe I've got, my favorite spot dog robot helping me do some stuff. And you're kind of witnessing this interaction. I look pretty happy in the corner. This is just like a normal day in the future where I've got robots that generally act as assistants that do things that I want in my house. Now, there's like a couple of problems with this in terms of just kind of seeing this interaction, right? So like what actually were we seeing? What was Spot giving me, like an orange perhaps? Like, is that what I wanted? Maybe Spot was like moving to this like specific location, right? Maybe I really like my robots to go through certain waypoints in my house. Or maybe I don't know, like I really just wanted it to pick up a fruit, and that was like the only thing that I really cared about because my table was cluttered or something like that, right? And so this is kind of like a central challenge that I want to illustrate as being a motivating example for some of the work that we'll talk about, is like from a demonstration alone, right? It's kind of like hard to truly understand what I really wanted in this task. And we're kind of, in the course of this talk, we'll explore kind of how this question can inform the way we think about building robots that work really well. Okay, so to zoom back out, this is me. I really want to build robots that act how humans want them to act. So, like moving past, my robot dog, maybe I've got a robot Atlas or something like that in the future, something much more humanoid and capable. I want to be able to exist in my space and have my robot kind of understand how to do my chores, how to interact with me, interact with other possessions that I hold dear in my house. And I want this to kind of all be seamlessly incorporated into my life without me having to kind of babysit the robot at all times, how to kind of do the things that I wanted to do. And so as we kind of maybe already have learned the lesson of, what humans want is actually really surprisingly difficult to specify. It's actually maybe fairly difficult to enumerate all the different reasons that we want robots to act specifically in all the ways that we want. And so, like, kind of, what are the paradigms that we have available today for doing this? Maybe in RL, we end up defining really ugly things that like look like this. We write either, reward functions or like features that parameterize reward functions for kind of exactly specifying all the different things we care about. And as we know, this is kind of not the easiest thing for an end user to do because it requires a lot of expertise. It's subject to, all sorts of misspecification, misalignment, kind of problems. Not to mention RL itself is kind of a challenging paradigm to deploy, in the real world. And so, okay, like RL of kind of like user specified reward functions doesn't appear to be the answer to our specification challenges. Okay, well, what about learning from demonstrations, right? Kind of this is, the direction that we're all really excited about right now. Um, Now, kind of the problem when we learn from demonstrations is that we're learning from demonstrations and we're kind of mapping directly from, well, nowadays, especially input spaces that represent, full visual inputs from the robot sensors, and we're mapping this directly to actions, right? And when we kind of deploy this learned imitation policy in new environments, we might hit new environments or characteristics that we haven't seen before. And all of a sudden, like our policy drifts off course and like disastrous things happen, right? Like, for example, we've got Atlas, it's maybe trained to like do parkour on this like course, but maybe the like wooden plank moves slightly more to the right than we needed it to. It's a new environment for the robot. And all of a sudden, the actions that we've memorized to perform just completely and catastrophically fail. So this is also bad. We're able to kind of elicit more general purpose behavior that like does more complex things, but like also not great for kind of solving some of the problems that we care about. Okay. Well, let's maybe take a step back and think a little bit about how humans represent the world, right? And so I was a cognitive science in undergrad. I think a lot about kind of how humans represent knowledge and communicate knowledge. And I think there's like a pretty rich literature that suggests that humans represent the world quite abstractly, right? So like take this kind of like very simple example. Um, so this is a map of Princeton, New Jersey, where the authors of this paper are from. And so let's just say from like a pure visual input perspective, we have like the map on the top. It has a lot of the details. It has all of the details, in fact, that we can capture surrounding a topographical kind of like view of the environment. Now, the authors actually did kind of a really clever study where they said, okay, well, depending on the task that we want kind of end users to do, perhaps on the left, we want users to bike around Princeton, New Jersey, and on the right, we want users to drive around Princeton, New Jersey. Like, think about what is the way you represent the environment in order to do that task. And the authors actually found that, like, in a series of controlled studies, that humans actually dynamically and flexibly kind of construct abstractions. They represent the world differently depending on the task that they're being asked to perform. And so I kind of argue that this is a very key insight that shapes the way we should meaningfully think about building robots, right? And so I think kind of the key takeaway from this type of literature is the idea that abstractions capture important features, kind of like abstract concepts or important reasons that explain why it is that we act in the world. And this is what kind of affords the generalizability and like flexible, fast, efficient new learning that humans kind of deploy when they enter new environments. And so what we really should be trying to do is like capture these features when teaching our robots. To kind of ground this back into the example I'd given previously, right? Like if, for example, I was able to tell the robot that actually the only things I really care about you performing this task is the fact that the object is in fact an orange, and that you are able to transport this object that is an orange to kind of this location, right? That would be able to abstractly specify important features that we care about for performing the task in a way that I want. And then we don't need to worry about kind of like these spurious correlations of like was the object, or sorry, was the robot kind of like moving to a different location? And so this is kind of just the key hypothesis that we'll kind of explore in a couple of these works today, is the fact that we, by we, I mean designers, not users, need to efficiently and reliably learn these human-aligned abstractions, because that's what kind of enforces really nice downstream behavior without requiring an excess amount of kind of like demonstrations or, labor for specifying tasks. I'll kind of pause here and see if there's any questions. Cool. All right. So, we're going to kind of like focus on couple of questions related to that general lofty goal today. So today we'll talk a little bit about, okay, well, we want to kind of do this, common sense knowledge teaching to robots, but like, how do we actually meaningfully do this in a way that's, reliable and efficient and doesn't involve, a ton of labor? And then, secondly, what happens if, specific users have kind of like implicit preferences that haven't been specified? What happens when we need to kind of do some sort of interaction with a specific user to understand what that abstraction might be for them? And then lastly, can we actually know when our learned abstractions are wrong and think about how to fix them reliably at test time? Okay, so we begin kind of our quest for common sense priors, and like where does that quest lead us? Well, it is the year 2024. And so naturally, the quest for common sense priors will lead us through natural language. So I work with, Jacob Andreas, who's an NLP guy, and something that we think a lot about in the lab is about how natural language is kind of like a very rich compositional operator, contains a lot of really rich compositional operators that help us understand not just kind of, how to communicate in the world, but actually the structure of the world. It's the idea that language reveals how different objects and entities relate to each other and how they should act in the world. And so in kind of just this example here, I've shown the idea that like, if you are a entity that possesses a key, then that tells us something about maybe the fact that you might be facing a door that is locked, that you might need to use this key to unlock. And so it's the idea that we can perform all sorts of fun hidden inferences over things that may or may not actually exist in the environment based on the way that we communicate. And so this is the kind of rich knowledge that we want to leverage when thinking about how to build usable human-aligned abstractions for communicating preferences and how to act in the world to robots. And so obviously, language as abstraction in robotics is kind of something that we're all interested in exploring today. And so let's kind of like briefly think about the different ways in which we've utilized this type of a paradigm in robotics. And so I probably, haven't, probably in the span that it took me to write this talk, we've had new works come out in the space, but, maybe this is a reasonable representative view of what we're doing today. Um, I think people have really explored the idea of using language to compose general tasks together in terms of like the things that we might need to sequence to perform a task, right? So, for example, if I want to do something like go to the red in the middle example here, go to like the final goal location through a certain environment. I might need to understand that in order to do so, I might need to go through like a sub door that's in the middle. I might need to, pick up a key that's required to like unlock a door. And then maybe with that like unlocked door, I can finally go through to my goal location or something like that, right? So I think it's the idea that we can use language to perform action abstraction, right? That different kind of primitives can be composed together to to act in kind of long horizon ways. Now, I kind of want to turn that paradigm, shift that paradigm slightly and say that, okay, well, language is certainly very useful for thinking about how we need to sequence larger steps together to perform higher level goals. I'm actually more interested here in the idea that we can use language for representing the world in the first place, right? Rather than figuring out, okay, given a language sequence, what's the right thing to be doing? I actually just want to know how I should be seeing the world. Like, what are the important elements or features that exist in my environment that we capture in order to actually represent our task meaningfully? And so, like, our first kind of foray into thinking about this as a paradigm was, the naive, simple thing, right? What if we just literally queried LMs for what are task relevant features? We just kind of like asked LMs to be our high-level task specifiers that identified important elements of scenes that we needed to construct abstractions. And so let's take kind of our, orange example with Spot from earlier, and say as a user, I kind of gave this like somewhat ambiguous instruction of like, bring me a fruit, right? And let's just say this first image here was like our observation of like what we wanted to be seeing from the scene. Right. We can ask the LM or a language prior questions like, is the color of the object important to the task, right? Are the objects themselves, like, what are their properties and identities? Like, are they important for the task? Maybe we can ask things like, is the shape of the object important to the task, right? The idea is that we can take kind of these grounded features that we extract from scenes and convert them into linguistic features that specify their value in terms of being important to certain tasks. And so given kind of like some answers on whether or not these questions, give yes or no answers, we can actually kind of construct a distilled state representation of what are the meaningful features in the environment that we actually care about for performing this task, right? So it's the idea, state representation, state abstraction has kind of been a pretty historical concept for thinking about representation learning in robotics, and how can we actually leverage human-like priors to do this automatically and quickly. And so this was our first work. We just call this LGA language guided abstraction, where given a state or observation S of kind of what our current environment is and a language specification of what maybe the user wanted, we can actually perform abstraction by saying, okay, given these kind of like unstructured feature representations in the world, we call this kind of our phi. Maybe there's water, there's oranges, there's drills, maybe they're located in particular points in space. Like, LM, like what is actually important for this particular language specification, right? And the LM can return kind of a slightly more structured feature representation that we can reground back into the scene. And with that regrounded abstract representation, we can kind of, carry on with our favorite policy learning technique downstream. We can, in our case, we do imitation learning, but you can, run your favorite like SECAN or whatever on top of this as well. The idea is that we are literally using a language prior to understand what are important human features that we should represent for performing policy learning. And this we'll see kind of is a very powerful idea that, will kind of rear its head later on. Okay, so we wanted to just see like how well this general premise worked. So we evaluated test and simulation. We were working in this, I think, what's the 7 degree of freedom robot arm kind of tabletop manipulation setting, and we were just asking it, various language instructions, things that ranged from kind of, specific things like bring me a pan to slightly more ambiguous specifications, like bring me something I might, be able to cook with. And the idea is we wanted to meaningfully capture to what level of ambiguity these language priors were able to ground specific elements of our scene into the desirable features that actually abstractly communicated what the human wanted. And so the first question we asked was, well, do these language priors actually construct good state abstractions, right? And so what we did was we took, a series of tasks in that simulated environment, and we varied the number of demonstrations we were generating as a result of as a result of humans, for example, demonstrating what to do in that situation. And we compared what we call LGA, so language guided abstraction, against your favorite kind of like imitation learning, goal condition imitation learning kind of baselines. And so here, the three relevant lines to be looking at are the colorful ones, the purple, blue, and pink lines, where LGA is the language guided abstraction. LGA Hill is actually the one where we ask humans to be able to refine the proposed LM hypothesis space. So the LM says, oh, I think these things are important. Like human, can you actually verify that like these things are important? And then the human, the blue line, is the one where we actually just asked humans to perform manual specification themselves with kind of no help from a prior. And we find that in all three situations, we actually perform far more efficiently given a finite sample of demonstrations than if we're just doing kind of raw imitation learning. And I think this makes sense, right? Like we're trying to create abstractions that capture general properties of the world without kind of fixating on features that may be spurious to kind of what we're trying to learn. And so naturally, we do expect that we would be able to learn more efficiently given fewer demonstrations from this paradigm. And I think importantly here, right, like I think because I'm a HRI researcher, I care a lot about making sure that, from the interaction perspective, like I, as the end user, am not spending a crazy amount of time babysitting my robot to make sure that they're learning properly. And so we also measure the kind of time spent on being able to learn good abstractions. And albeit LGA Hill, which is the ablation where we had humans kind of refine the hypothesis, definitely was less time intensive than having humans do this from scratch. The fully autonomous versions were in fact, like by far the least time intensive interaction experience. And so I think this kind of illustrates a different axes of trade-offs that we also might be concerned with, is like how much time does it take to be able to meaningfully define these representations, and how does that kind of intersect with performance? And so kind of takeaways here are that we are able to outperform kind of like raw BC on task performance while also reducing the user time spent compared to, your typical manual feature specification. And so this is a nice little, middle area between meaningfully representing symbolic structures of the world, but also making sure that it's not, a super non-flexible way of doing so. And then secondly, we wanted to kind of see whether or not these language priors actually improve the policy robustness, right? Like we're claiming generalization, like does that actually kind of in practice happen? And so we perform a series of experiments where we take the same tasks that we've learned on before, and we kind of create a set of state covariance shifts, where perhaps if I needed to pick up a heart from like a previous task, what if I added some distractors into the scene? What if I like change the color of the heart or something like that, right? And we find that on these kinds of covariate shifts in observation space, that LGA, the kind of abstract representation we're learning on, does in fact perform a lot better with respect to generalizing to unseen environments. And we see the same thing with kind of multitask ambiguity. So when we have multiple linguistic specifications, such as, for example, bring me a pan versus bring me something I can find in a kitchen versus something, bring me something I can cook with, like, are we able to meaningfully represent multiple specifications of potentially ambiguous linguistic specifications for a particular task? And that also makes sense considering, if we're kind of doing raw goal condition behavior cloning or something like that, where we have no way of flexibly adapting to a new linguistic specification that we might be seeing at test time. And so what's also really nice is that we are, in fact, the representations that we're constructing are more robust to these kinds of shifts in kind of what we might be seeing from train to test. Okay. And so a couple of fun robot videos of us kind of just demonstrating this in work. Uh, if we wanted to, for example, at train time, oh, sorry about the noise, throw away leftovers from, the table. Yeah, so, we identified that there's maybe like a leftover water bottle or something on the table, and we want to be able to put that in what we think is like a reasonable disposal bin. And then at test time, in fact, instead of seeing the water bottle, we see something like an orange, right? And maybe we see something like a compost bin instead of like a recycling bin. We do find that there's, some meaningful non-trivial generalization properties that we are able to actually see in scenes in real time. I will mention here that for the purposes of running these robot demonstrations, we did not perform like imitation learning on like the kind of raw and effector space. We did have like slightly higher level primitives, such as like grasp at particular locations that we were learning off of. And with those kind of like high level primitives, we're able to generate the demonstrations that we saw here. Cool. Now, it doesn't kind of take, that much reading in between the lines to know that, while an interesting idea, it's certainly very limited, right? So kind of LGA, the abstraction framework I've presented here, is actually very limited in the sense of it requires kind of comprehensive task specification in the language command, right? Like we are able to reasonably query for important features, given the fact that our linguistic specification, what the user was telling us, actually meaningfully captured everything that was important for the scene, right? And so I'll kind of go through examples of where this is not going to be always the case, right? Okay, so imagine, we as the user, I wanted the robot to do something like throw away the can.
Actually, Andy, could I ask a quick question?
Yes.
It's related to this too. So it's even related to like the comment you're making in the last part, because I was trying to understand a bit more about how these, like where the information or details come for these abstractions, because there must be some information about the task or something in there that makes it give some particular option, because it's not like throw away the can. Is it not told what the can is, or is there some vision model? Or is it given like information about the primitives that the robot has in order to be able to kind of glue together like the representation and the task it's being told to do?
Yes, great question. So I'll move back to here. I'll maybe keep it on the scene here. Yeah, so for the particular purposes of this demonstration here with the real robot, so we assume that we had access to a certain set of primitives, and those primitives can be at any level of abstraction that you choose to specify, right? But the idea is that we don't have like labels necessarily for those primitives. So maybe I have the idea that I can like grasp, like I can manipulate the arm to XY pixel location and like pick up a bottle, but I don't have the ability to like caption what that is meaningfully. But what I do have is the ability to learn from demonstrations that show that type of behavior. And the question is, okay, what is the right representation to be actually deploying that action on, right? So imitation learning, it typically maps from, state, like full state, to action. And that action, again, can be anything that you want it to be. And what we're doing here is we're just saying, okay, given a linguistic specification of your task, such as throw away the can, with knowledge that my environment, my particular observation contains, for example, like a water bottle in a can and a drill. What we do is we construct kind of an abstract state that says, okay, well, what are the relevant features that are important for throwing away the can? Obviously, the can would be important, but maybe like the drill on the table is not important, right? And so it's the idea that we're able to, given the specification of the task, distill our full observation space down into something that's slightly prettier and structured that filters out some of the spurious correlations available in the scene. And then we perform your typical imitation learning on top of it. So the actions, you can copy whatever you need. It's just the idea that the actions are related better to like a cleaner, prettier version of the observation space. Does that make sense?
Yeah, that helps. I think that covers pretty much everything, because I was just wondering about the part where, I guess, is it the imitation learning process, not the language model, has got the concept for understanding what a grasp is. Because you're saying
That's
like
exactly
grasp.
right. That's right. It's the
Okay.
idea that there are certain ineffable qualities of acting in the world, right? Such as like grasp at this particular end effector joint location, that it's like kind of hard to specify in language, right? But the general idea of grasping is something that we care about. And so if we can just relate the abstract notion of bring me something with the particular kind of, more low-level details of like how actually that action looks in practice, that we can meaningfully kind of get the best of both worlds. We kind of preserve learning from demonstrations while also making sure we're acting in a slightly better representation space, that we're not, over memorizing details in the observation. That's like the general idea here.
Okay, great, thank you.
All right, I'll move back to here. Okay. Yeah, and so great question. And a pretty clear limitation of that type of thinking is the fact that we need to be able to actually specify all the things we care about when we ask the robot to do a particular action, right? So let's take, for example, the demonstration on the left here. We just watched, Spot pick up a can and like walk across the room and like throw it into the trash can, right? Okay, that seems reasonable. But what if, the demonstration on the right also happened? Okay, now all of a sudden this gets kind of interesting, right? Like we, with the same language specification, just saw two very different types of behaviors being demonstrated. Like a question that I have is, well, like as a human user, you're seeing this, like why? I'll just cold call on people. Sasha, like why do you think in these two different environments the demonstrations might have differed in the way that they did? Like what could be an important feature that is explaining this difference?
An important feature that explains this difference. I mean, the difference is one is longer than the other and like kind of less efficient. It's not taking a short path.
Mhm.
I don't know. Does the object behind the robot matter? I'm not sure. Is
Well, I
like a
think that
drill
that's kind
there?
of a question, right? Yeah. Is, well,
Yeah.
what if we actually kind of had these implicit preferences, right? Let's just say in the first example, I don't particularly care about the robot stepping on, say, my shorts, because I don't know, like they're dirty shorts on the ground, like it's fine, whatever, right? But in the second case, all of a sudden, I really do not want my robot dog, stepping on really important valuables. I do not want the idea that maybe my electric drill might interact really poorly with kind of my robot stepping on it, right? So all of a sudden, now we have this kind of latent preference or implicit preference that's parameterizing why the my abstraction representation of these two tasks might be very, very different, right? Like what happens in this situation? And this is kind of, the next line of work that we're going to kind of unpack a little bit here. Okay, so first, bear with me. I like probability, and so we're going to kind of give a brief probabilistic view on what inference problem we're actually faced with here. Okay, and so right? Let's think about the problem from like an inference perspective. Let's just say humans sometimes in environments hold latent preferences over preferred abstractions, right? Maybe in the situation on the left from previously, the S hat, the abstraction I cared about, just, had the can and like the trash can because those are the only task relevant features that meaningfully describe what I care about. But in the example on the right, all of a sudden the drill is like really, really important, right? It's not just the trash can and the can, but like the drill is actually meaningful for thinking about what are important properties of my environment. So like this is the inference problem, right? Given, our state, our natural language instruction, and kind of like this hidden preference theta. You can think of them as reward parameters, you can think of it as whatever, some sort of hidden preference. Like what is actually the abstraction that we should be constructing over that type of a problem, right? And so in LGA, what we effectively did is we modeled this problem minus the theta, minus the preference. We said, okay, let's think about the probability of our abstraction given just the raw state in the language instruction. And we're going to go ahead and take like the argmax, the most likely explanation for what the abstraction might be. Now, what we actually want in a situation like what I'm describing here is the argmax given our hidden preference theta as well. So this is kind of the new inference problem that we actually want to be dealing with. What is the most likely state abstraction that explains the fact that we are faced with our state, our language description, and also this hidden preference theta? That's what we're going to kind of get after here. And so kind of our key insight when thinking about kind of the exercise that we just all went through together is the idea that, like changes in human behavior, like we actually can derive more meaningful evidence from just watching demonstrations, right? In the two demonstrations that we just saw, the change in behavior tells us there must have been a change in what's important in the environment, right? Like there's something about the environment, there's some feature that's hidden there that's changing the way we act. And so naturally, there must be a preference over the abstraction that we're constructing to act in that environment, right? This is kind of like the key idea. Like contrastive demonstrations meaningfully tell us something about the world. Now the question is like, can we actually infer what these things are? I'll use the word implicit here to kind of define the idea that, maybe there's like a latent preference that exists in mine as the user's head that we need to somehow query out of me without me telling you in language what that is. And so, right, like this is the type of like implicit inference that we're going to try to go after here. Okay. And so this was some really recent work that actually I was super excited about because I think this was a good first step towards thinking about how to solve a problem. Okay. So at train time, we keep our kind of like same abstraction training motivation, but instead we're going to provide an additional piece of evidence. We're going to say, okay, given two contrasting demonstrations, right, like the ones that we just saw, and the language description that kind of, describes both of them, like, was there a difference in how the human decided to demonstrate that task, right? Was there like a delta variable? Was that like 1 or 0, right? Like, was there a difference? And then given that delta variable, we can actually also use that to help the LM query for whether or not there are important features we might be missing. So we can say, okay, given the fact that these are the two representations of our environment with that specification, and the fact that we know that the human acted differently in it, we can ask, like, why is this behavior different? We're literally asking the language prior to give us theta. Like, what is theta? What is the hidden implicit preference here? And it turns out, actually, I think, maybe unsurprisingly, maybe surprisingly, I'm not sure, that language priors are actually really good at this too. With respect to general human preferences over how we choose to act in different situations, like LMs are quite good at being able to meaningfully capture what those might be. And so in this case, GPT maybe gives me something like, I prefer to avoid electronics rather than, preferring to step on shorts or whatever, right? And so with that information, we kind of carry on with our abstraction generation like before. We say, okay, well, given that we have this preference of preferring to avoid electronics, all of a sudden, like, what are important features that might be relevant in my scene? And in the scene where we have drills, right, the LM's like, oh, like the drill is in fact an electronic. This is obviously very important for kind of the task that we're trying to perform here. And so we construct our representations like follows. In one scene, we represent maybe, shorts on the ground. In the other scene, we don't represent the drill or something like that, whatever. And we say, okay, let's carry on kind of with our abstraction construction like before. And so at test time, maybe faced with new objects in the scene, we can understand how to meaningfully see whether or not those features engage with kind of our preference function. I'll pause here. this, I think there's a few different pieces that are intuitively important to understanding what we're doing. And I just want to kind of make sure that we're all on board. The critical thing here is that preferences are sometimes latent, but behavior tells us something about preferences. And then with those preferences, they can inform how we construct abstractions.
So just small piece of clarification here.
Yes.
The delta variable here, is it informing this query that the case with the drill was the longer one, or it's just saying 1, 0, were they different? So like these are different, why?
Yeah, that's an awesome question. So in an ideal world, we definitely, the first query is definitely more informative than the second, right? We decided to do the second just because we actually struggled a lot to think about like whether or not it would be reasonable to caption to also ask the idea that like behavior be captioned for the LM. And we decided first like no, this was like not reasonable, and so the only thing that we actually used was the notion that behavior was different. But I think like in general the idea of trying to also describe why behavior is different could be really meaningful. And I think we have some ideas for how to do that, but we did not do that here in this work. But yeah, awesome question.
Yeah, I'm also sort of wondering about like the scalability. Like obviously the example you're showing is like really clean. There's like one difference, and that difference is the underlying like causal factor that's causing the discrepancy. But in reality, in a cluttered scene, there's going to be like lots of things that it might be much, much more difficult to like disentangle. Do you
Yeah,
think that
that's
like an
a
LLM would still be able to handle something where there was a lot more complexity?
Yeah, so we had done experiments where, and I'll go through this next. We had done some experiments where we added up to like 3, 4, 5 distractor objects, and we found that it was like pretty good. I don't know how that would kind of, I haven't done kind of like the analysis on like how and when that scale breaks. I think in general, like in household kind of scenes, like there's usually one or two specific reasons that we seem to be seeing behavior, really, really matter for explaining a preference. And LMs are actually really good at giving like really large unfiltered scenes, like a very succinct kind of abstract reason for what that is. And so, for example, like we gave it drills, we gave it laptops, we gave it iPads, and like it was able to all meaningfully in all those cases say, oh, actually, like electronics was the problem. And so there's a form of like abstraction that's going on inside of the LM when we ask it to give us a preference query as well. And we found that that was like pretty good, albeit we didn't really like push it to crazy extents.
Sorry, maybe one last question, if I may.
Yeah,
Um,
totally.
so the output here, like let's take this example. We have prefers to avoid electronics 0.8 and prefers to step on shirt 0.2.
Hmm.
So are those like output values like probabilistically fused into the training part, or is this like now encoded as a 0, 1 preference between electronics and shirt, for example?
Yeah, that's a great question. I think either is reasonable. We chose to do the latter because it was cleaner. But yeah, I
Yeah,
think
I
both
think
are
the
reasonable.
probably the former is like a little bit perilous because you're really relying on the calibration now, which is like a much bigger bar to achieve rather than just like
Exactly.
the ordering.
Exactly.
Yeah.
Yeah. So we did the latter, but I think the former is, merits exploration as well. In fact, what we did
Okay.
was actually we set a particular threshold. So the LM gave us, like some entropy threshold over what its confidence was, and we set some threshold that said, okay, like if you gave us an answer that was over this confidence, we would just take the argmax of that. But if not, then we would do something else, and I'll talk about what we do after this. So
Okay, thanks.
cool.
Right. Maybe I'll ask a really quick question then, because I guess you keep saying this is an LLM here, but there's like images and videos for the behaviors. So what is the input to the LLM? Do you convert that into text to describe what the behavior of the robot was?
Yeah, great question. So actually, when we were doing this project, VLMs were like not great. So we did not try raw images. What we did is we took an image captioner. Basically, we took I think DEDIC. We said, okay, like given this image captioner of a segmentation and image captioner model, like we took that structured representation and we passed that through the LM. So it gave us things like objects, their captions, their relative positions, things like that, and we just gave that whole kind of like raw JSON to the LM. But nowadays, we actually have been doing some stuff with VLMs, and they're like okay. And so I think there is a path forward to doing this with raw images. It remains to be seen whether or not, it works that well. So yeah.
Okay, thank you.
Well, and we kind of performed, very similar simulated tasks for evaluation, except this time we kind of, for each of the different sweep, place, whatever tasks, we endowed a series of kind of hidden preferences. Things like pick up a fruit, but make sure it's like the ripe fruit, right? Maybe place the mug down, but like make sure it's not put on like, an electronic, or maybe sweep the food into the sink, but like avoid like a hot stove if there's like a hot stove there or something like that, right? So a series of kind of just like artificial tasks that were designed to get at the idea that there might be hidden human preferences at play. And so, we wanted to see like, can we do good inference on these kinds of tasks? And we generally see that yes, in fact, across at least the more common sense tasks that we tested, such as, preferring certain types of objects to others and wanting to avoid sharp and like hot objects, LMs were able to reasonably capture that in the preference query. And so, yeah, we outperform kind of the raw imitation learning baselines from before, as well as LGA, which is the previous framework that we presented. And then now this is kind of getting at the question that that Liam was asking, which is like, what happens when preferences are like slightly ambiguous, right? Like I've so far presented like very clear, easy, like kind of common sense, duh preferences. But like, what happens when like the things we're asking are like a slightly weirder than what might be kind of like natural? And so what I mean by this is if I ask the user something like this, right? Like to pick up my like favorite food, or maybe put the mug down on like my preferred dish, right? Maybe like avoid like special objects, right? Like maybe I have like a particular valuable that like only I care about, right? Like, are we able to meaningfully understand how that uncertainty unfolds, like in the query process? And so the question we asked was like, okay, well, do these priors query for use and preferences like when like things are kind of ambiguous? And so the first kind of like sanity check we performed was, moving back to kind of the 0.8 and 0.2 values from the previous slide, like we wanted to understand how notions of like uncertainty or entropy actually existed in LMs. And so what we did is we constructed, these kind of ambiguous tasks, and we contrasted them to the more like, so, common sense general tasks. And we wanted to see whether or not the LM had even an idea that its own estimate of the preference function that humans held was actually different in these two cases. And we found that actually it reasonably was able to at least differentiate between the things that we were asking it, right? So in the ambiguous task, we found that there was like a pretty significant difference between the LM's own confidence estimates over what it thought was the correct answer versus the more general cases. And I actually think this is actually like a very powerful idea. It's the idea that like we have these really nice structured common sense priors in natural language, but we also want to understand when those priors might be unsure of like when they're right, right? And so we seem to be seeing some evidence of the fact that we can disentangle the two in some of these cases. And then for, kind of these ambiguous tasks, we wanted to kind of see whether or not a version where we additionally asked the LM to verify their answer of the human was able to meaningfully outperform cases where it didn't choose to ask humans. And so by active PLGA here, I mean active in the sense of the LM sets its own entropy threshold for uncertainty. If it doesn't, surpass a particular threshold, it says, oh shoot, my answer must be like kind of not good. And so I'm not confident enough in my own preference function. I need to query the human. And so in those cases, the active version of our algorithm asks the human, hey, like, is this actually the correct answer? So it's like verification of a hypothesis that we think is correct. And so I think this is really important here because it shows that we can model uncertainty and learn good abstractions from preference queries in cases where we need to ask the human for additional help. And so it's kind of this like interactive deployment at test time that's meaningful here. And then some more fun robot videos. We had a lot of fun at Boston Dynamics doing some of these demos. If we kind of take the avoid like electronics case from before, we can test on kind of new objects in rooms like pants or like laptops. Yeah, there are versions of this where we did this with slightly more cluttered scenes, but this was kind of the cleanest version. And so we found that, by learning that we wanted to avoid electronics, that we can meaningfully represent things like laptops and iPads and things like that in the scene and like deploy the appropriate behavior. And then for something like, I don't know, place the drink in the bin, right? Let's just say during training, I had this preference that, okay, I want cans in trash cans. If like I don't have an alternative. But if I had an alternative, right? If I had a recycling bin, I want the robot to actually place the can in the recycling bin. Can it kind of generalize to new objects and like goal locations as well, that kind of thing. And lastly, again, do we find that when users are communicating with robots about their preferences, is this in fact a better interaction experience than kind of existing alternatives? And so we kind of did our favorite NASA TLX cognitive Likert survey at the end, and we found that on a number of more qualitative, subjective user experience questions, that general people obviously preferred communicating their preferences in natural language versus kind of needing to specify features by hand or something like that. And so in general, natural language is a very natural way of communicating with the world. And in conjunction with some of the queries that we are making to these pre-trained priors, they're able to meaningfully generally improve on the user teaching experience than kind of previous paradigms that we had. Okay, so I'm almost out of time here. Sorry, I took longer than I thought I would. Some next steps. We're actively working on some of these things now. Questions on like how do we actually tell if our learned abstraction is wrong, right? Like or right or wrong. We think we have a best guess. Like, are we actually sure? What happens, when there's lots of things and we're not actually sure what the right answer is? Can we do this iteratively, right? Like certainly there's this idea that we can be performing, we could be improving in kind of a loop. Like I propose an abstraction, the human is like, no, this is wrong. I go back to the drawing board and I update the abstraction. I go back to the human's like, oh yes, this is better now. Like how do we do this iteratively in a way that doesn't involve, catastrophic failures at deployment? And then that's lastly, something I'm really interested in is like what happens when kind of our knowledge prior, our like LM conflicts a lot with individualized user feedback. Like what happens, like how does that tension resolve? Especially when we're thinking about very kind of like more niche ineffable qualities of behavior that we might not be able to capture in kind of these pre-trained models. And so many thanks to the Boston Dynamics AI Institute for lending us Moana, this spot robot here, for running many demonstrations very late at night. And then awesome collaborators that I was very fortunate to work on some of these projects with. Cool. And that is it. Thank you guys for listening.
All right. Thanks so much, Andy. Okay, do we have any questions for Andy?
I've got a question.
I had one, but like the next steps slide kind of answered it. We were playing with, they were not quite, the same as your abstractions, but last summer we were using a language model to kind of figure out which objects in the scene were safely traversable by a mobile robot. Kind of the issue here is like and then we would just remove the non-traversable objects from the map so the robot could plan through the objects that are safe to traverse, right? That was the general idea of the pipeline. But that's a very binary thing, and we always needed a student to kind of check the abstraction before actually deploying the robot to make sure that it was kind of reasonable, right? So we needed an external verifier, in that case that was me, before actually running the robot. So yeah, I think kind of figuring out when the abstractions are wrong and how to incorporate this in a feedback loop is very important problem here.
Yeah, I actually think I didn't touch on this at all, but like interpretability, right? Which I think nowadays is a bit of like a loaded term, but interpretability actually I think is afforded really well when we work in these symbolic state spaces. There's this notion that all of a sudden I don't need to, have a user look at like a reward function or like something slightly more challenging to be understanding what the robot might be doing, right? Like you have some sort of at least a guarantee on if you're representing the relevant information for acting correctly. And so my kind of hypothesis is I think that will do wonders for general interpretability as well.
Okay.
Well,
I think Luke had a question.
Yeah, we got
Yeah,
people online.
yeah. So it seems like you're sort of putting a lot of trust in the language model's ability to represent its uncertainty. Because if it's sort of incorrect, then your state abstraction might end up sort of canceling out information that's actually really important for the task. So I'm curious, like, if you think this is a good idea, just asking the language model how certain it is about the correctness of its abstraction.
Yeah, I mean, that's a really good question. I think this is, a question that not just we are dealing with, but kind of the entire world of AI is dealing with right now, right? Is like how do we like what is the actual amount of trust we place in these things? I think right now my like kind of canned answer, I know it's not that interesting, is that I think we have to think about the right application areas for deploying these things, right? Like maybe it's okay that my LM is like picking up a pear instead of like an orange, right? Maybe it's okay that it like crashes into my coffee table, right? But it's maybe not okay if like, I don't know, it's helping terrorists build bombs or something like that, right? I just think that like understanding how these interaction protocols actually ground into specific situations that you're looking at and kind of thinking about what's like the worst possible thing that could happen, right? And maybe doing like a regret-based approach on like understanding that would be helpful. And so I think it's important to think about the context in which you're deploying these things too.
I wonder
Yeah.
if I could ask a quick follow-up, if that's okay. I know there's another
Yeah, totally.
question, but could you go back to the slide where you actually showed like the entropy as a function of
Yeah,
like
totally.
ambiguity? And
Okay.
so maybe you could just explain in a little bit more detail exactly what you're showing here. Like what was the actual experiment that you did and how did you evaluate the entropy in this case?
Sure. Sorry, give me 1 second. Sorry, I like don't have the ability.
It's the downside of fancy slides. Fancy slides, it's always hard to I have the same
Yeah,
problem.
I like can't click through my slideshow for some reason, so I'm trying to make it there. Oh, sorry. Oh man, it's gonna take a while.
Yeah, here. No, not quite.
Okay.
Okay,
How
well,
do I...
either way, there's like a graph
Yeah.
where you had entropy on the y-axis,
Mm-hmm.
and then on the x-axis, there was like, it was two bars. One that was like an ambiguous,
Mm-hmm.
and like not ambiguous. I forget. It wasn't not ambiguous, but whatever word.
Yeah, yeah,
And you showed that like
totally.
the entropy was higher for the like ambiguous case. So what I understood was that you're asking for preferences, like, is this better than that? Can
Yes,
you
we are
just
literally,
sorry.
yeah, I think we're almost there now. There we go, almost. Yeah, so the experiment we did here is we generated a family of tasks where the specifications were kind of ambiguous, or like kind of the latent preferences were like very ambiguous, right? For example, like me trying to infer what your favorite food is slightly harder than me inferring that like hot stoves are bad, right? Was kind of the hypothesis. And so what we did is we constructed a family of tasks where the latent preference was meant to be really ambiguous, and then a family of tasks where things were like a lot more common sense. And we ran the full pipeline for the preference query abstraction. And we found that in the cases where we're asking the language model to guess at what the hidden preference was, and we asked it to kind of model its own uncertainty over its answer. Whether or not it would even recognize the fact that I was asking for my favorite food was like a harder question that was more ambiguous than if I was asking it like whether or not people generally prefer like ripe fruits, right? Does that make sense?
Yeah, I'm sort of still a bit confused though about how you actually evaluated the entropy. So the evaluation of the entropy itself was also determined by the LLM, Or did you
Yeah,
actually like look at some kind of probabilistic values and then evaluate the entropy over the
yeah.
or
So
some
we asked the LMs to output a vector of their guesses as well as a probability for those guesses, and then we computed the
okay.
entropy over the answers. Yes.
Okay. Interesting.
Okay, I think we had
Thanks.
a question from, oh, sorry.
Yeah,
Yeah,
exactly. From Puyan.
from Puyan.
Yep. Thanks, Andy, for your great presentation. I have a general questions. As I know, and in your presentation, you mentioned we as a human, we use abstraction learning in high level phases to make the definition of states to be real less complex for ourselves. At the same time, our life actions heavily depends on our learned affordances from the objects. I mean, regardless of the, for example, the geometry or color of the objects, we learn affordance to do actions. For example, pick a mug, we can do the same actions for all the same mugs or everything like that. So I want to know your opinion about that. Do you think this concept, I mean, learning affordances, object affordances, can be combined to make a robot's decision making and actions in the environment more efficient, or do you think they are separate concepts?
Yeah, that's a great question. I think that I didn't touch that much on this question, but I think both are meaningfully important, right? Like I think state abstraction and representation abstraction is like important independent of action abstraction, right? And so I think what's important is like the idea that we can develop strategies that allow us to kind of compose the two together, right? For example, like you could have run like all of this stuff with not imitation learning over like continuous actions, but over like primitives, right? And so like the idea of your kind of typical action abstraction framework, pick your favorite SIGCAN or whatever model. And as long as you're able to understand how the affordance relates to representation, I think that's where you kind of get meaningful generalization properties. So I think both are important. And I think that explorations into like best ways of combining the two, I think would be valuable. Albeit I think that does start conflating some questions together. And so I think it's also important to kind of disentangle some of these things when studying them in controlled settings too.
Thank you.
I had another question
Okay,
if we have time. Do we have time?
I
Does
think we
anyone need to
do.
Eddie,
I
do you
could
need to
stay all
go?
day. No, I could stay all
Okay.
day, so it's up to you guys.
So I remember this paper from Anka's group like maybe 5 years ago at least. I think the
Uh-huh.
first author was Andrea Bajci. I don't know how to pronounce her name. I'm
Bye,
sorry.
Chi.
Baichi. And the idea was like, I think there's some nice connections with what you're working on. Like it was like, okay, we want to like move a coffee cup, and there's this like implicit kind of constraint that like that when we move from point A to point B, we shouldn't spill it. And this was formulated like through an inverse reinforcement learning type of formulation. And so I guess my general question is like, have you thought about inverse reinforcement learning as a framework for incorporating these kind of like language abstractions in and learning preferences? If yes, great. If no, why do you think it's not the right way?
Yeah, awesome. This is literally the project we're working on right now, and so this is super
Okay.
apt. Yeah, so I think we've kind of explored imitation learning with abstractions here, but I think you could also do reward learning with abstractions, right? So in your typical IRL setting, I mean, this is also the problem with IRL, right? Is that we've typically mapped from raw demonstrations in state space to rewards. And obviously, if you're doing weird things like, I don't know, always moving to like a weird waypoint when you don't need to be, your reward function that you learn is going to capture the fact that the robot really wants to move to this weird place, even if it wasn't actually important, right? And so what we're trying to do here is do an iterative kind of abstraction update with IRL, where we say, okay, like maybe from this demonstration and our set of features that we seem to think are important, let's learn the reward function. And let's see what the policy produced from the reward function is. And if that policy is not going to explain our behavior, then we know we've like missed something, right? Either we're missing a feature or our abstraction is wrong or like something is off here, right? Like, does that make sense? It's like if
Yeah, it
I'm
makes complete sense.
and so that's kind of like the direction that we're moving in now is trying to think about how we use IRL iteratively to learn when we're missing features. And we're going to use the LM to basically try to propose features that explain why demonstrations are different for reward learning. And then we kind of learn rewards on top of those features. Yeah.
Yeah, very cool. I mean, a practical limitation seems to be in general with IRL that you have to like heavily parameterize the reward function in a way to make it tractable. Do you still have the same problem here? Like you need some prior over what the possible reward terms are going to be before you start, or is there a way to generalize this?
Yeah, I mean, that's definitely true. And I think this is where you think the language prior can be useful as well, right? It provides initialization of your feature space, and then you learn IRL on top of that feature space. And if that feature space is
Yeah,
wrong, then you might ask a human why it's wrong. Yeah.
very cool. Makes sense.
Yeah. It's definitely a slow slog, and I think there's like a lot of IRL is just not the cleanest. And so trying to get it, wrangle it within abstraction learning is like kind of a challenge.
For
So
sure.
thanks so much.
Yeah, thanks so much. Great talk.
Thank you. Take care.
Take care.
Bye.
Yeah, see you around.